Hi everyone, my name is Robbie Robinson and I'm presenting on mixed load performance indexes. And in this graphic here, this represents a plate loaded in both tension as well as bending. And that is what's meant by mixed load. The paper's title is Extension of Ashby's Performance Indexes in Mixed Tension Bending Solicitations by French researchers and published online in Advanced Engineering Materials. The scope of the paper is the derivation of a mixed loading performance index. And the key question is, can a performance index be developed for low mass and high rigidity in plates under mixed tensile and bending loads, which would better address real-world applications? Meaning, as we've been studying the performance indexes, it's often for a single load, such as a tie in tension or a beam in bending, where real-world applications, more often than not, are under mixed load conditions, such as a beam that's in both tension as well as bending loads. So to address this and potentially develop a more applicable performance index, and here is our model. Again, the plate loaded in both tension as well as bending. The authors modeled the deflection in the plate when loaded in that mixed case scenario as a differential equation. And here's that. And the solution to this was used to develop an exponential function for stiffness in that mixed loading case. And so the concept, again, as we've been studying the single load conditions for stiffness, Young's modulus over rho, and that's in pure tension. And for bending would be Young's modulus to the third over rho. And they're reasoning that if it's a mixed load condition, that our performance index should be some combination of these two. And they're proposing that it is Young's modulus raised to alpha, which is some exponential function over rho. And through the solution to this differential equation, they develop alpha to be 1/3, which represents the bending condition, plus the second term here, 2/3 tangent, and this F2 to F1 is a ratio of the tensile force to bending force. And when this tangent term goes to 1, this becomes 2/3, and alpha becomes 1, and that represents our tension condition. When tangent goes to 0, we have no tension force. This alpha remains 1/3, and we have a pure bending condition. And the authors reason that it is known that when you have a ratio of double the tensile force to bending force, that you can approximate this mixed load as a pure tension loading case. So they developed this formula for mixed loads, and to prove that out, they would expect, since in real world applications it's known that as you approach double the tension to bending load, that you can approximate the load as a pure tension load, that this alpha would approach 1. So in proving that out, you can see as the tensile load increases relative to the bending load, alpha does indeed approach 1. And then we have our Ashby's chart here, plotting Young's modulus across density. I've added 2 performance index lines, one for pure tension, one for pure bending, and I've left the material in between the two in color to better call out that optimal material choices change when you move from tension to bending loading. So all these materials that are colored now change as we mix our loading condition. So our alpha, and in turn the index, now become functions of this load mix ratio here, this F2 to F1. Another thing that can be pulled from this graph is that plates loaded in tension don't need to be as stiff as those loaded in bending. And in summary, Material indexes don't have to be only for a single condition, and they can be developed to be functions of variable conditions. Plates in loading or plates in tension require less stiffness than those in bending, and the research would have benefited from greater explanation of the method that they used for the derivation of the performance index, as well as further identification of potential next steps for future research efforts, or a discussion of the limitations of the current method. The demonstration that these indexes can be used in real-world scenarios increases the material index concept's utility and should promote its use. Thank you very much.